It's my great pleasure to introduce Luca Delacretaz. Luca was a PhD student in Stanford, where he works with Sean Hartnell, and that's also where we met, I believe. And now Luca is, I think, in my old office in the University of Chicago, where he is a McCormack Fellow. Maybe a few words about his work. So the way I understand his work is he works on effective field theory, both in hydrogen condensed matter physics. It's difficult for me to gauge. I think now he's tilting more and more towards low energy and some condensed matter physics. And I guess today he'll tell us about application of his ideas to one-dimensional chiral transport and fluctuations.
Right. Yeah. Okay. Thanks. Yeah. Thanks for the introduction and for the invitation to speak here. I do hope to come visit you guys at some point in the future. Let's hope not in the too far future. But it's nice. It's nice to meet some of you virtually already. So yeah, this talk will be about hydrodynamic fluctuations. So before I tell you what these things are, let me just kind of give you an overview of what I'll say so that you have an idea of the plan and where I'm going. So as I'll explain, hydrodynamic fluctuations can be weak or strong, depending on the situation. And what I mean by weak is that in many contexts, we'll see that interactions between hydrodynamic modes or kind of nonlinearities are irrelevant, so that they lead to only small corrections to the late time physics in many situations. And when that happens, it means that we have a systematic framework called fluctuating hydrodynamics, which is kind of like an effective field theory to make predictions, to look for systematic corrections to the leading behavior. And often in these systems, we have, for example, diffusion. And so you could look for corrections to diffusion. So this part will mostly be an introduction to the next part. But I will also talk about an application of this controlled effective field theory from this paper, where we used it to resolve a recent puzzle in the apparent slow thermalization of spin chains in one dimension. So then I'll talk about strong fluctuations, and I'll tell you what type of systems have strong hydrodynamic fluctuations. And in particular, I want to focus on the edge of quantum Hall systems. And I'll try to convince you that these systems have large hydrodynamic fluctuations. And they lead to, in these cases, what strong fluctuations mean is that the hydrodynamic interactions are relevant. So they lead to a breakdown of diffusion, and you no longer have a controlled effective field theory. And instead, they lead to new dissipative kind of behavior or universality class, which looks like this. So a non-diffusive kind of spreading of modes, a super diffusive spreading. And we'll see that it also leads to anomalous and singular transport on the edge. And so this is a paper from last year with Paolo Glorioso. All right, so let me first convince you about why you should care about hydrodynamics. So the reason we care about hydrodynamics is that it's really ubiquitous. It's thought to emerge in any interacting system, whether it's quantum or classical, at finite temperature and late times. And which form of hydrodynamics will emerge will just depend on the symmetries of your system or the conserved quantities. So for example, if you have conserved energy or charge, this often leads to diffusion. And then sometimes if you have conserved momentum, this will lead to the Navier-Stokes equation and so on. And what's really striking here is that the hydrodynamic description doesn't at all care about the microscopics, so that very different microscopics can lead to the same hydrodynamics, like cosmology and condensed matter systems can have very similar hydrodynamic descriptions, because hydrodynamics only cares about the symmetries. So the first question that comes to mind is, how is such universality possible? Why does it emerge always, and why does it only depend on symmetries? And I don't think we have a rigorous answer for this. But the intuitive explanation is that at finite temperature, in an interacting system, most excitations relax at a time scale that I'll call the thermalization time. So that if you wait for a long time, you're not left with much and your system becomes simple. The only stuff you're left with are things that can't relax because they're conserved. So for example, the total charge in your system cannot change. And for a similar reason, a long wavelength modulation in charge density will have very slow dynamics. It's going to have a decay rate proportional to some power of its wave vector. So that as long as we work with small enough wave vectors, so that we look at long distance physics, these modes, these these densities will be parametrically longer lived than generic excitations. So then hydrodynamics is the late time description of these coarse-grained densities. So let's see how it works in the simplest possible case, where I have a single conservation law, like charge. So then hydrodynamics will be a theory of this conserved density. And sometimes people like to work instead with the associated potential, the chemical potential. And it's going to be subject to this continuity relation, the conservation law. So this continuity relation also involves a current. And the current operator itself is not slow. Its time derivative is not given by the gradient of something else. So it's not a slow operator. On the other hand, we expect it at late times to be carried by the only stuff left in the system. So the slow degrees of freedom, the densities. So the idea of hydrodynamics is basically to express this current at late times as a function of these slow operators in the most general way possible. And in a gradient expansion, because we're interested in the long distance physics. So the leading term you can write down will look like this. And it comes with some coefficient that I don't know that I call D. So now that I have this equation called the considered relation, I can plug it back in the continuity relation and get an equation for charge. And linearizing around some background will lead to some 2-point function of charge that looks like this, that has this diffusive form. So it has a single diffusive pole at imaginary frequencies equal to minus IDK squared. So it's important to point out that there are two expansions happening here. There's a gradient expansion in these dot, dot, dots. And this expansion is always controlled, at least in principle, because you can always go to long enough wavelengths, look at small wave vectors, so that these higher gradient corrections will lead to only small corrections. But there's also an expansion in fluctuations of the charge density. And this expansion is more subtle. In fact, it's only going to be controlled when hydrodynamic interactions are irrelevant. So this is one of the main questions that we want to answer first. You probably know that hydrodynamics leads to more than just diffusive modes. Another very common mode in hydrodynamics is a sound mode. For example, a sound mode arises if you have conserved momentum. Let me just show you an example of a system that has a sound mode. If I have conserved energy and momentum, energy density and momentum density. So I have continuity relations for both of these quantities. Here an energy current, tau here is the stress tensor. So again, these conservation laws involve the currents, which are not hydrodynamic densities, but we can express them using considered relations back in terms of these densities, and then again solve for the correlation functions. And so if you do this, so this is, for example, would describe a fluid, you'll find that the response function of momentum this time has again a diffusive mode in the transverse channel, but it also has a sound mode. So it's a pole that has a real part as well, and then with some sound attenuation. So if I plot these things, this is how it would look like. I have a diffusive mode and then a pair of sound modes like this, and that's what their dispersion relations look like. So if I perturb my system, and the diffusive mode will just spread diffusively, whereas a sound mode will propagate ballistically and have some diffusive spreading. So these types of modes arise all over the place in many different types of systems. Diffusion describes the physics of heat in basically any material, but also in some cases particle number or things like spin. And sound is also very common. I'm using sound to communicate right now. In superfluids, there's another type of sound mode, and there are also sound modes in systems with spontaneously broken symmetries, transverse sound in a solid, and so on. Of course, it's not the only types of modes you can get in hydrodynamics. There are some more exotic modes. For example, in anisotropic systems, you can have modes that look sound-like in some direction and diffusive in another. This happens, for example, in smectics. There are also modes that have a real part that starts as k squared. For example, spin waves in a ferromagnet, and more generally what some people call type 2 goldstones. And because of Andrea, I think I contractually have to say that fractons would also probably go in under this list. So there's a lot of exotic modes you can have, but I'm going to focus on these two types of mode, diffusive and sound modes, because we'll see that a lot of rich physics already happens here. So I want to ask about hydrodynamic fluctuations for these two types of mode. And the central question I want to ask is, when are these fluctuations big? So let's start with the diffusive mode. So this
Well,
is
can
our,
I interrupt you for a second?
Yeah.
Can you, for those of us less enlightened, say a few words about what hydrodynamic fluctuations are before saying why they're
Yes.
big or small?
Yes, yes, yeah. So what they are nonlinearities in your densities. So yeah, let me show you this right now. So this is our diffusion equation, okay? And so the point is that to get this dispersion relation, what we did is that we linearized it around a background charge density. But of course, you know, things like the diffusion constant will depend on the charge density. And so really so you know, the diffusion constant is allowed to depend on the charge density. Anything is allowed, the equation of state, the pressure, and so on can depend on the charge density. And so these will lead to nonlinear terms in this equation. Okay, so if I expand, for example, this diffusion constant around a background charge density, it will lead to an equation that the leading order is just the diffusion equation, but it's going to have a leading nonlinear term, which looks like this, okay, which involves a derivative of the diffusion constant with respect to the charge density. So this is what I would call an effect of charge fluctuations, okay? It's nonlinearities in the dynamics of hydrodynamic densities. So I'd like to ask when this term is important, when it leads to big corrections. And there's a simple scaling argument that will tell us. So basically, we'd like to compare this term to the leading, you know, kind of kinetic terms here. So we'd like to know how charge fluctuations scale, how these fluctuations of the charge scale with at low frequencies. And to do this, all we need to know is what the charge two-point function is. Okay, and so in a diffusive system, the charge two-point function looks like this. It's a Gaussian that spreads in time. It's basically what I plotted over here. And this overall power of time you can get by remembering that if you integrate this charge density over all of space, you get the total charge. So that has to be conserved. So that better give you a constant. Okay, so that, and that's what integrating this Gaussian will give you. It's going to cancel this power of time. So this teaches us that charge fluctuations scale like 1 over t, or like frequency, to the d over 4. D is the spatial dimension here. Okay, and in a diffusive system, omega goes like k squared. So this is like wave vector or gradient to the d over 2. So if we look back at this equation, we have our two linear terms that have the same scaling because kind of by design. And then this nonlinear term just has an extra power of charge fluctuation, and so it's going to have a higher power, a positive extra power of wave vector k. So that at very small wave vectors is going to lead to small effects, small corrections. So the bottom line is that in some sense the critical dimension is 0 as long as we're above 0 dimension. So in any case of interest, charge fluctuations are small in diffusive systems.
Can I have a question?
Yeah.
So, okay, so if I look at your diffusion equation, the first line looks quite familiar. So if I take d as a constant, take it out of the bracket, then all I have is a Fokker-Planck equation, right? With no convective term, right?
Right.
Okay, so then you said, well, the diffusion constant in many cases depend on the local density of the stuff that's move around. So then it's possible that when you have more jam-packed system that is diffused smaller, for example. So then you take a derivative on that, so that gives you a delta n term. That term to me looks like the convective term in the old Fokker-Planck equation.
I'll talk about convection in a bit.
Okay.
This is not, so this won't lead to ballistic propagation.
Okay.
If that's what you're, yeah. I'll talk about a ballistic. So this is still, it still has two gradients.
But which one is bigger though? One is the direct gradient on density. The other one is the second derivative, right? So I assume the second derivative is smaller, right? So then therefore, yes, the first derivative would be bigger. So that first derivative is convection, right?
So here there's still two gradients. There's still two powers of the gradient.
I understand. The delta square term, if it's smaller, then this term will be dominated by the delta n, right? Which is the first order derivative on density, right? Which is locally is a convection.
Yeah. I think maybe you're, so in the ballistic case, there's exactly this that happens, where yeah. Okay. So let me go exactly. I think you basically anticipated what I'm about to say. I think that's right. So yeah, let's look at the ballistic case. So the ballistic case, as we were just saying, there's not just a spreading of the front. There's a ballistic, there's a kind of speed of sound. So this is what the equation of motion of a density, for example, would look like. So we looked at what happens when you expand this dissipative part, but now there's a term that has one less gradient. So it's going to be more important in at low energies, and it might be more dangerous. So let's look at what happens when the speed of sound of this mode depends on the density. So let's again expand it, and we have this nonlinear term. Okay, so notice it has one less gradient, but one more power of charge fluctuations. So let's try to figure out when this term is important. So let's again do a quick scaling analysis. So first, just to simplify things a bit, it's helpful to follow to work in coordinates where we're following the pulse, so that we basically just see it spread diffusively. So in these coordinates, this kinetic term simplifies to simply this. And now we can use the same scaling analysis we had before. Now we just have diffusive spreading in these coordinates. So our charge 2-point function again looks diffusive, which tells us that charge fluctuations again scale like k to the d over 2. So now let's plug this in this equation over here. So again, our two kinetic terms go like k squared, but this term, it has, as we said, it has one less gradient and one extra power of charge fluctuations. So it's not necessarily smaller. It's only smaller at small wave vector k if the dimension is larger than 2. So we have a critical dimension of 2, and for dimensions smaller than 2, it's going to lead to big effects at low energies. So the bottom line is that hydrodynamic fluctuations are weak for diffusive modes and for ballistic modes in more than 2 dimensions. And they're strong for ballistic modes in less than 2 dimensions. Okay, are there any questions about this? Okay, so I'll start by giving you a flavor of how this this fluctuating hydrodynamic works in situations where fluctuations are weak. There we have a kind of perturbative handle to make systematic predictions, and then I'll talk about an interesting case where fluctuations are strong. So in the case where fluctuations are weak, so for example, in diffusive systems, in any diffusive system, what this means is that we can basically expand, for example, our considered relations and powers of the densities, of hydrodynamic densities, and systematically look for corrections to the leading diffusive behavior. And this framework is called Fluctuating Hydrodynamics. It was developed a long time ago, and essentially in these papers. It has an even longer history. And I won't need the details of this formalism, but what they found is that to kind of write down an effective field theory of these hydrodynamic degrees of freedom, there's a doubling of degrees of freedom. For every charge density, there's a noise field whose fluctuations are tied to dissipation through the fluctuation dissipation theorem. So they're given by the diffusion constant. Recently, there's been a kind of revisiting of this effective field theories for fluctuating hydrodynamics. And what I really like about this more recent formulation of fluctuating hydrodynamics is that it makes really clear where this doubling of degrees of freedom is coming from. And basically what they explain is that we're doing real-time thermal physics, out of equilibrium thermal physics. So we're time evolving a density matrix, and the right way to do that, a thermal density matrix. And the right way to do this is on a Schwinger-Keldysh contour. So you naturally have a doubling of degrees of freedom on both legs of your contour. And under RG, these two legs will start coupling. So at the end of the day, you have a theory with two copies of your fields that are coupled. And how this maps back to the older framework is that basically the average of these fields corresponds to the hydrodynamic densities, and their difference maps to the noise fields. So I won't really need this formalism. I just want you to keep in mind that it does exist there. For the purpose of this talk, there's a kind of simpler way to study these hydrodynamic fluctuations without the full formalism and to get the kind of qualitative results. And the approach is simply to say, well, I know that there's a kind of effective field theory out there that's Gaussian at very low energies with some small interactions. And so what I can do if I want to compute correlation functions, for example, of my currents, is simply to write down a considered relation like this, expand it in charge densities, and then Wick contract or Gaussian factorize my charge densities, because I know that they're approximately Gaussian. So let's see how this works in practice. Let's try to compute the current two-point function to compute the conductivity. So to leading order, I'm going to have this linear overlap with the density, which gives this diagram. And I can use my density propagator that I gave you before, the diffusive correlation function, to just get this leading term. And what you find is that, as is well known in a diffusive system, the DC conductivity is just some constant given by the Einstein relation. But then there's going to be a one loop correction to this coming from this nonlinear term. And if you compute this loop, again, using the tree level diffusive Green's function on the legs, this will give you this fractional power of frequency. So it gives you a non-analytic contribution. And notice that it's a positive power. So at very small frequencies, it's less important than this leading constant. Okay, this is again reflecting the fact that interactions are irrelevant in diffusive systems, so they lead to small corrections in the IR at very low frequencies. There's also in general corrections coming from higher derivative terms, higher derivative corrections. These are always analytic. The non-analyticities come from loops. So even though this correction is small, smaller than the leading term, it's still interesting. One reason it's interesting is that it's the leading non-analytic term. And another is that in low dimensions, even though it's smaller than this leading term, it's larger than the next correction in hydrodynamics. So it might be visible, in particular in one dimension. In fact, it was seen in this paper where they did exact diagonalization in a one-dimensional interacting lattice system, and saw a kind of 1/√√ correction to the conductivity at small frequencies. So these small corrections due to hydrodynamic fluctuations to transport go under the name of hydrodynamic long time tails. They were actually discovered in classical numerics originally, a very long time ago, and that numerical discovery is what led to the theory of fluctuating hydrodynamics. And since then, they've been seen in quantum systems, and there's been interest in them also in the high energy community for their possible relevance to the quark-gluon plasma.
I have a question.
Yeah.
In the equation, do you know how to explain the deep at zero?
I think they comment on it. I think it's a finite size thing, but yeah, they definitely comment on it. They know how to explain it. Yeah. All right. So as a mild extension of this equation, I'd like to compute this again, but at finite wave vector, because it's going to be useful for later. So let's compute basically the current two-point function at finite frequency and wave vector. And you can do this. We did this in this paper. So this will lead to kind of universal correction to diffusion. And what you find is that the charged two-point function, for example, looks basically diffusive, but it has a kind of self-energy correction, which looks like this. It's non-analytic. It's the same non-analyticity that we saw before, but now we can see it as a function of both wave vector k and frequency. And what's interesting is that it has a branch cut with a branch point not at the diffusive pole, but halfway to the diffusive pole. At these frequencies here. So this might remind you of the of your QFT textbooks of the analytic structure of a weakly interacting field, a massive field. So it's a massive field will have a two-point function, will have a pole and its correlation function at the mass of the field. But if it's weakly interacting, it's also going to have a branch points at energies at which it can start producing particles, two particles. And so there's a simple argument to find the location of the branch point, which is just the onset when you can cut your diagram and get physical states. And there's a similar argument to find the location of this branch point without computing the loop, which is just to take this loop diagram, cut it, and impose that both legs be on shell, meaning that they satisfy the diffusion equation. And if I impose both of these equations and fix the wave vector k, this will lead to just after 2 lines of algebra, you'll find that the branch point has to be here. So with this formula in mind, now that we have this formula, we can actually, what's nice about it is that we can Fourier transform it to get the charge 2-point function as a function of time and space as well. So that will be useful. And it has this form. This is the leading diffusive behavior, and this is the one loop correction. So before I move on to the quantum Hall systems, let me just show you a quick application of this fluctuating hydrodynamics to a very simple system. So I'm going to apply it to this Heisenberg spin chain, the classical Heisenberg spin chain in 1 dimension. So the quantum version of this problem is integrable, but the classical version is thought to be non-integrable, and although its thermalization has been debated for a very long time since these papers. And this debate was recently revived by this paper, which led us to look into it in more detail. So this system has a little more symmetries. It has time translation invariance, so it's going to have a conserved energy density. But it also has SU2 symmetries that just rotate these spins. So it has, it's going to have 3 conserved densities associated with SU2. But otherwise, the hydrodynamics is basically expected to be the same. At a linearized level, you would just expect all of these densities to diffuse. And so since we're in 1 dimension, diffusion means 1 over square root of t, decay of. So if I look at the 2-point function of spins at the same site, but at late times, it should decay like 1 over square root of t. And that's indeed what the numeric sees. So here I'm plotting the 2-point function of either energy density or spin as a function of time. And you see that it decays like 1 over square root of t to very good approximation. This is classical numerics, so you can really do amazing simulations. Finite size is not an issue. And these things are very precise. In fact, they're so precise that this group noticed that that there seems to be a slight deviation from this 1 over square root of t. So if you try to extract a diffusion constant from these plots, so you would just multiply this correlation function by square root of t, and then you take the square. This should spit out the diffusion constant. So for energy diffusion, it seems to equilibrate pretty fast to some finite value. But for spin diffusion, it seems to just keep on growing here on this logarithmic scale with time. So it led them to suggest that there was some kind of anomalous super diffusion or logarithmically enhanced diffusion in these systems. But now let's go back to our fluctuating hydrodynamics. What hydrodynamics really predicts is that there will be corrections to 1 over square root of t coming from high derivatives and from loops. And in 1 dimension, the leading correction is coming from a loop, and it looks like this. Of course, fluctuating hydrodynamics is like an effective field theory. It doesn't, you don't know the coefficients that appear in your effective field theory. They're Wilsonian coefficients, but there is still some naturalness that tells you that that leads to some expectation for their order of magnitude. So we expect this dimension-full thing to be of order the thermalization time, the cutoff of hydrodynamics. And so, in fact, if you plot this quantity here, so just square root of t times c, for exactly the same data, so the blue curve here is the same data as this thing. Here I'm plotting it versus 1 over square root of t, so the very late time is over here. You see that it asymptotes to some finite value, as expected by diffusion, and the leading correction seems to be linear in 1 over square root of t. And in fact, the slope actually is roughly of this order of magnitude. So it seems to be, this slow thermalization is really just a manifestation of nonlinearities of fluctuating hydrodynamics. Okay, so that's all I wanted to say about the kind of situations where fluctuations are weak. Maybe I'll pause here for questions, and then I'll move on to the main topic I want to tell you about.
What is the value of?
Yeah,
go ahead.
I guess I'm a little confused here. Okay, so so this suggests that there's a breakdown of equal partition principle at some point in time scale, right? So at which point, so the Einstein diffusion constant would suggest that the system is thermalized.
Yes.
When you have terms that seem to exist beyond the the Einstein diffusion constant. So almost effectively to say that this Einstein diffusion constant is time dependent, which is supposed not to be.
Right. Yeah, I wouldn't say that. I wouldn't say that it's. I agree that it looks like there's that things are thermalizing very slowly, or that there's like a lack of thermalization. But it's not quite that. It's rather that what thermalization really means is it means emergence of hydrodynamics, and hydrodynamics isn't just a linearized theory. It has fluctuations, so it comes with these corrections. But it's true that it means that thermalization is subtle. So, for example, let's say you wanted to define thermalization, the thermalization time as saying, oh, I take a non-conserved operator and just look at its decay in time, and I expect it to be exponential, and so this will be the thermalization time. Well, typically, because of these hydrodynamic tails, in fact, that's how they were discovered. People took an operator that they expected, was not hydrodynamic. They took the total current, and it decayed instead of exponentially. It decayed polynomially because of these effects. And this doesn't mean that things aren't thermalizing. It is thermalizing. It's just that it's hard to avoid hydrodynamics. Hydrodynamics is polluting many correlation functions. They're subleading corrections to hydrodynamics also pollutes things. So thermalization means emergence of hydrodynamics, and that happens rather quickly in interacting systems. But hydrodynamics itself has many corrections to just the leading diffusive answer.
If I just take your equation, let's say imagine that I shoot a particle into the system as a test particle.
Yeah.
So if my external driving force is very small, then very quickly these particles will be bounced around by the particles in the system, will be completely governed by the diffusion equation, right?
Not quite. It depends. If your particle couples to charge density, it's actually going to relax very slowly.
I'm thinking that the rest is not charged. Let's say you have a neutral system,
yeah,
a neutral diffusive system. I'm shooting a particle that's charged, so I can manipulate from the outside. Okay, I can apply electrical field, for example.
Yeah.
So if I drive this test particle in this diffusive system, if my driving force is very small, then what I'm going to have is a particle that will acquire the Einstein diffusion constant of the system very quickly, right?
Yes, that's right. If your particle is charged, then indeed it will. Yeah, it will relax very quickly. Yeah.
Okay, so now if I apply a driving force to make it move really fast in this driven diffusive system, then all your diffusive system will appear as some viscosity constant, right? Some viscous drag, right? Some Stokes coefficient, right?
Perhaps.
So I guess I don't know what happens going from slow drive to the fast drive in between. I always thought this transition is, I took it for granted. I thought it was all understood. From your talk, it seems to be, this assumption is very dangerous.
Yeah, I'm not sure what happens with a fast drive. I mean, that's beyond hydrodynamics. If your drive time is fast compared to the thermalization time, then hydrodynamics itself won't tell you necessarily what's happening. This is kind of like far out of equilibrium physics.
Okay.
Yeah, maybe we can chat more later. Maybe I didn't completely understand the question. Yeah, thanks for the question. Okay, so in this last part, I'd like to focus on the edge of quantum Hall systems. So as we all know, these edges support gapless excitations, and sometimes they're formulated in terms of CFTs or chiral liquid channels. And as theorists, we often like to think of the edge at zero temperature. But on the other hand, it's been known for a while that thermalization is crucial to explain experiments. In particular, the experiments that don't see, the experiments don't seem to see all these chiral liquid channels that are predicted for some fillings. Instead, the only long-lived quantities on the edge that they see are associated with conservation laws. So they see charge and sometimes a heat mode. So this tells us that the edge is thermalizing, which implies that we expect a hydrodynamic description. So the question I want to ask is, what is the hydrodynamic description of the edge at small but finite temperature? And here I want to emphasize that I'm not going to assume translation variance. So momentum is not conserved in any approximation. The only conservation law I'm going to use is charge conservation, and later I'll talk about energy conservation as well. And the beauty of hydrodynamics is that that's the only input you need.
Will you assume boost invariance?
No. I'm not even assuming translation variance.
Oh,
forget about boost.
Sorry, zoned out.
Yeah.
Okay, fine.
This is dirty, dirty system. What I'm saying is going to be robust against a fair amount of disorder. All right. So yeah, so the beauty of hydrodynamics is that all you need to know is that the system thermalizes, and then you need to know the symmetries. What are the slow quantities? And then it kind of gives you completely microscopic independent predictions. So this question was already addressed in this paper a long time ago. And within a linearized hydrodynamic approach, what they found is that charge fluctuations propagate ballistically on the edge. This probably won't surprise you, and have this diffusive spreading. So what I'll show is that because of hydrodynamic interactions, this diffusive spreading is never stable. Hydrodynamic interactions are relevant. They lead to a breakdown of diffusion and instead trigger a flow to a new dissipative fixed point, which is in the so-called KPZ universality class. And in particular, this kind of chiral charge on the edge, so it still propagates ballistically, chirally, but has a very different decay rate. It decays like its wave vector to the 3/2, which is the dynamic critical exponent of KPZ, rather than k squared like in diffusion.
So, can I ask you, what is the meaning of K if no translational invariance?
Yes, good. Yeah. No, that's a fair question. So I'm not assuming that momentum is conserved, but I am assuming that things are homogeneous at long distance scales. So that, I don't. Otherwise, it's true that everything could depend on X.
Yeah. This case along.
But they are really badly disordered on large distances. We know that there are multiple scales controlling disorder, with the biggest apparently being 20 micron. So no sample can be seen as uniform in any sense, because you don't have samples longer than a millimeter in this game.
Yeah, good. So depending on the length scale, depending on how the length scale of disorder, and there may be several, compares to this thermalization scale, thermalization length. Either I'm treating it as being too microscopic for hydro, so I don't care about it. But indeed, if it's larger, then what I would say is I would just solve diffusion equation or whatever replaces the diffusion equation in a system with profiles of stuff, and you can do that. You can do hydrodynamics around assuming long wavelengths. So both limits can be treated. Very short wavelengths and very long wavelengths disorder. Of course, if you have a mix of everything, it's harder, but at least both limits can be accounted for.
Can I assume the case along the tangential direction of this circle?
No. Yes, tangential. Yeah, exactly.
Okay.
Yeah. Thanks.
And then you assume this is an infinitely large system, so then therefore the curvature of the path of the matter. Okay.
Yeah. Well, let's first do that. Yeah.
Okay.
So can you estimate what in which temperature your formalism is correct?
Yeah, good. Yeah. So I definitely want the temperature to be lower than the bulk gap, so that I keep that the bulk just still doesn't do anything.
But you also still want it to big enough so that the thermal length is not too short.
Exactly.
So do you know what is the exactly?
Yes. So if whatever your temperature is, indeed, if your temperature is very small, this 1/4 thermalization time, in the best, let me just talk about the best possible case. This will be roughly a order of temperature, and then you would, well, whatever that is, it's telling you that the physics that I'm telling you about will happen for frequencies smaller than that temperature. Frequency smaller than that temperature.
I would argue that this thermalization time is normally at least 1 divided by the square of the temperature.
Yes, you're absolutely right.
In some systems, it's much greater than even that. So that's another issue. When you go to the scaling regime, when temperatures are low, this equilibration length tends to diverge very rapidly. And that was seen experimentally. No one has a quantitative dependence of the equilibration length on the temperature. But when people measure thermal conductance, at least at 2 thirds and 5/2, the divergence is obvious. And at 5 5.5 is extremely fast. So which is probably is related to the theoretical prediction that 5.5 this goes is actually 1/t to the fourth. So extremely fast divergence.
Exactly. So for example, if your edge is let's say it's a CFT, of course there are going to be relevant deformations of the CFT. They're going to be relevant, irrelevant interactions on top of the CFT. And in these situations, you know, the thermalization time isn't just temperature. It's temperature in a case where it's a completely, so in a case where you have basically a weakly coupled system or a CFT that's, you know, doesn't have collisions plus irrelevant interactions, it's suppressed by an extra power of temperature divided by some microscopic scale. And that power depends on what the mechanism for thermalization is. So typically, indeed, this will be temperature to some power divided by the microscopic scale. So it might be that you have to go to very small frequencies to see this. But I'll be talking about this region, about this frequency region. Frequency or wave vector. So one consequence of this KPZ universality class is the dispersion relation for this collective modes. Another is that it controls correlation functions like transports at low frequencies. And for example, it leads to a singular optical connectivity on the edge, which diverges with this power frequency, 1/frequency to the 1/3. So this is very unusual to have non-analytic transport at low frequencies in a thermalizing system, usually precisely because of hydrodynamics. All the correlation functions at finite temperature are kind of boring. They have simple poles because hydrodynamics kind of takes the non-analyticities of your zero temperature system and puts them, for example, in the temperature dependence of transport parameters. But here, precisely because of the breakdown of hydrodynamics, this leads to non-analytic and singular low frequency transport. So these are the two main results of this. There's a number of extensions that I'll mention. As I said, one can talk about heat, how heat moves, and one can show that heat diffusion similarly breaks down on the edge. And then I'll mention how to extend this to higher dimensional systems.
What do you mean by heat diffusion breaks down? The heat
does not. Sorry.
It doesn't diffuse.
It doesn't diffuse.
Why?
Because of hydrodynamic fluctuations.
And then so you will have one spot that's hot, then the rest of the system?
I didn't say it didn't move. It does do something. It just doesn't. It doesn't go like omega equals minus idk squared. It's a different power basically.
Okay, so you will still if I create a local hotspot, the temperature of that spot will drop. It's just not following the same diffusive law. Okay.
Exactly. Yeah. Okay. So let's see let's see what the hydrodynamic treatment of this problem is. So let's start with just charge. So again, we have a single continuity relation for charge. Except the difference now is that we have the anomaly, the chiral anomaly for this U1 symmetry related to the filling of the bulk. And here I'm suppressing factors of 2π and so on. And this anomaly, a simple way to understand it in these systems is from inflow from the bulk. If I turn on an electric field, because of the Hall connectivity, I'm going to start to drive charge to the edge. And so from the perspective of the edge, it's going to look like there's non-conservation of charge. Okay, so it's been known for some time how to account for anomalies in hydrodynamics. And what happens in this paper in particular, and what happens is that they fix terms in the considered relations for the currents. So that in this case, the considered relation for my current will again have the same diffusive term like before. I wrote it in terms of the chemical potential this time instead of charge. But it's going to have this anomaly is going to fix this zero derivative term in the considered relation for the current. And so it's going to have an important effect, right? Because it doesn't have any gradient. So we can again plug this equation in the continuity relation to get an equation of motion for charge. Instead of looking diffusive, now we see that there's a ballistic front. The speed of sound of this front is related to the filling, but it's not universal. It also depends on microscopics through the charge susceptibility. So we can again treat this at the linear level first and linearize around a finite background, and this is what was done in this paper. What this leads to is a Green's function that looks almost diffusive, very similar to the diffusive one we had before, except that the pole is shifted by a real part given by the speed of sound. So that our collective excitation on the edge is, for example, right moving and spreads diffusively around that front. But now, as we know, in ballistic systems in one dimension, we have to be careful with nonlinearities. In particular, the fact that the speed of sound, since it's not universal, can depend on density. So if we expand it, there's going to be this term, and we saw before that this term was relevant. So yeah, this is just reminding you that this term is more relevant than the leading dissipative term. So what this is telling us is that in these systems, charge fluctuations are relevant. They lead to breakdown of diffusion, and we no longer have control, perturbative control on the late time dynamics of this. So what can we do? Well, one strategy could be to reduce the strength of these interactions by going to higher dimension, by making them less and less relevant. And in fact, going up to the critical dimension, which we saw was 2, and then do some kind of epsilon expansion, maybe to find the new fixed point perturbatively, and learn something about d equals 1. I'll talk about this in a bit. In fact, the theory in d equals 2 is also interesting in its own right because it describes stacked quantum Hall systems. But can we hope for more? Can we be more ambitious? Can we hope to learn something exact about the true dissipative fixed point in one dimension? And the answer turns out to be yes. There's some magic, even though there's a relevant interaction and no small parameter in the game. There's some magic in one dimensions. And I think the first paper that found this was this paper by Forster, Nelson, and Stephen in what's called the Burger's equation. This equation goes under many names. It's probably mostly famous under the name of KPZ, but all these things are basically the same equation. And it turns out that we can actually map our equation to this KPZ equation. So let me, for those who know the KPZ equation, let me just quickly show you how the map goes. So this is our anomalous diffusion equation. We have a chiral ballistic front, diffusive spreading, and a nonlinear term. Let's again simplify this equation by following the pulse, so working in coordinates where the pulse isn't moving, so that our kinetic term simplifies to this. And now this equation just directly maps to the KPZ equation, where charge maps to the slope of KPZ. So for those who aren't familiar with KPZ, KPZ describes surface growth. For example, if you burn a sheet of paper, how the front grows. So the degree of freedom there is the height of the surface. And here we see that the gradient of the height is what maps to charge density. Okay, so what we learn is that charge fluctuations at the edge of quantum Hall systems or chiral systems are in the Burger's KPZ universality class. So we can import all this knowledge about KPZ to this problem. In particular, one important factor of KPZ is that it has this dynamic critical exponent c equals 3/2. So let's see what KPZ scaling implies for our systems. So it tells us that the collective mode behaves like this instead of spreading diffusively. So we still have a chiral ballistic mode, but instead of spreading diffusively, it spreads a bit faster with k to the 3/2 instead of k squared. And moreover, a kind of surprising thing about KPZ is that the analog of a diffusion constant is entirely fixed in terms of thermodynamic quantities. And I really like this expression because it shows the 3 ingredients that were necessary to lead to the breakdown of diffusion and to this KPZ physics. The first is temperature. We're talking about stochastic physics at finite temperature. The second is the anomaly. Remember, if we didn't have the anomaly, we wouldn't have this ballistic mode. So we would just have diffusive spreading and their interactions are irrelevant. And finally, we needed nonlinearities in the form coming from the dependence of the speed of sound on density through the susceptibility. Let me mention that KPZ physics is known to emerge in one-dimensional hydrodynamics, so with full fluid hydrodynamics with momentum. But in these cases, it's crucially dependent on the fact that momentum is long-lived. So if you put on a little bit of disorder, momentum is going to decay and you'll lose all your KPZ physics. It's going to regulate all these IR kind of effects. Here, this does not rely on momentum being conserved. So it's robust. It should be robust against disorder. KPZ universality will also control correlation functions. So for example, the charge 2-point function is going to be given by this so-called KPZ scaling function, which is not known analytically, but it's known numerically to very high precision, and its limits are also known. So this is basically what replaces the diffusive 2-point function of charge in these systems. We can use this, for example, to compute the optical conductivity on the edge from some limit of this Green's function, and this is how you get the 1/, frequency to the 1/3. And the coefficient is entirely fixed.
So did you verify that this expression gives the correct fluctuation dissipation theorem?
Yes.
So it does at all omegas?
Yes, yeah. Mm-hmm. Yeah, and it satisfies the usual sum rules that diffusion would have satisfied.
Mm-hmm.
Okay, so it leads to this result, and here really the numbers, you can even get the numbers from these known numerical expressions for the KPZ equation. Okay, so let me say a few words about heat. So energy is of course also conserved, although experimentally it might be a little, well, it's harder to observe typically, and also it might leak out, so you have to make sure things are well insulated and so on. But so if we assume that heat is long-lived on the edge, then let's see what happens. So let's first ignore all thermoelectric effects.
Can I pause for a second?
Yeah.
Just a follow up on Dima's question. So you said that the fluctuation dissipation theorem is still preserved in this case. Mm-hmm. So which means the diffusion constant is directly linked with the viscosity, right? So if I have a test particle in the system, the diffusion constant of the system, according to Einstein relation, will be kBT over gamma, right? The gamma is the kinetics.
Well, not quite. The diffusion constant no longer plays a role. So dissipation is not controlled by the diffusion constant anymore. In fact, it doesn't appear at all in this expression. So fluctuation dissipation theorem here doesn't impose a constraint on the diffusion constant, but on observables in these correlation functions. It ties fluctuation of charge to dissipation, and here there's no diffusion constant. It's gone.
So where your faith in the preservation of the fluctuation dissipation theorem? So what makes you believe that's still respected here?
So you can look at the retarded Green's function for charge, and the symmetric 2-point function, and they will satisfy fluctuation dissipation. They will be related in the usual way.
Okay, so this is essentially Kramer's-Kronig relation, right? Isn't it?
Yes. Yeah.
Okay, so you said that's a guarantee of. Okay, all right. Okay, yes, let me think a little bit. Okay.
Yeah. In the diffusive case, yeah, that's a special case of that check, but here it just amounts to checking this.
Mm-hmm. Okay.
Okay, so now I want to incorporate heat. Let me first ignore all thermoelectric effects just to have a first simple take on this problem. If I do that, then charge does its own thing, heat does its own thing. And so then if I have both in the bulk, I have both a finite Hall conductivity and thermal Hall conductivity. Both heat and charge are going to propagate chirally with some velocity. And then the same story holds for both of them independently. So they're both going to have large fluctuations and a breakdown of diffusion, and I'll get two decoupled KPZ fronts with two different velocities.
Can I ask you a comment here? You mentioned that we deal with quantum Hall effect at the filling factor one sort. Of course, we know that the edge reconstructs in real samples, but you are dealing with very large scales. And at the filling factor one sort, the standard expectation is that only one chiral mode survives at large scale. And here you have two different velocities. So how does this square with the existence of a single mode?
Yeah, good. So in situations where you have a single mode, if you believe that the edge is really described by a single chiral Lettinger liquid channel at 0 temperature, then probably that's just not going to thermalize. So there, I think, if the theory is spot on, then I think it probably won't thermalize, at least if you don't have counterpropagating modes. Yeah.
These things that irrelevant operators are useless. So we have a finite
Yeah.
temperature, we have a bunch of irrelevant operators, all
Right.
powers of the gradient.
Yeah.
That will not thermalize it.
I think not. If you have a single, yeah, if your theory is chiral, I think even irrelevant operators might not help. So it might be harder. Yeah, it's probably harder to thermalize. I mean, they will do something, but I expect it's going to be harder to thermalize such a system.
Mm-hmm.
So, but you see here, it's kind of, so indeed, if you definitely, you know, if you've confirmed that this is the edge theory, then I think you prove that it doesn't thermalize. But here I'm saying, okay, I don't know what the edge theory is. Let's just say it thermalizes. And, you know, for nu equals 1/3, it might not be a good assumption.
Can it be that U2 velocities are actually the same in that case?
Are the same?
Yes, can it be that they are just the same when you have a single mode? And maybe this solves the paradox.
Mm-hmm.
In the standard description, of course, heat and charge travel with the same with speed. Then we have all these irrelevant operators that do some mass out of the propagating pulse, but the center seems to still with the same speed.
I see. You're saying in the case where the single.
You can solve it. You can solve it exactly still for the lowest order irrelevant operator, and you get some sort of a wave packet that expands as an area function.
Yeah.
So the center still moves with the same speed for everything.
Yeah. That's interesting. Yeah. So maybe, okay. Maybe, so here I kind of assumed it wasn't because I had some, you know, thermodynamic factors that come in here, and I didn't actually look into what these were for specific cases, but you're saying it might be natural in some situations.
So could you remind what is this chi? So what is that thermodynamic factor? So we take sigma xy and divide by chi. So what
this is the charge susceptibility and compressibility.
And CV cannot depend on filling factor in such situation, but chi should if that theory is correct. So because sigma xy does. So what is chi?
This chi is the charge susceptibility, charge compressibility. dN by d mu.
But it's related to sigma xy by the. Oh, I see. But then it's related to sigma xy by the fluctuation dissipation theorem. So probably your two velocities are indeed correct. Indeed equal.
In general, you're saying?
So no, for a single channel system. So I would think that xy divided by CV is the same no matter what your filling factor is, in the lowest approximation at least. And now when I look at sigma xy, which is exactly quantized, this thing is related to that exactly, this chi is related to sigma xy by the exact fluctuation dissipation theorem, hence also exactly quantized. And then it looks like you just get two identical velocities.
Yeah. I think that sounds pretty reasonable, that for a single channel, you should have the same velocity. But so it means that what I'm saying isn't straight off wrong, but on the other hand, I probably don't expect this model to thermalize. So you probably wouldn't even see diffusive spreading in this situation. I would expect, or it would be very, very suppressed because it's so hard to thermalize.
Of course, we can argue that in the absence of upstream modes, there is another challenge, that the way how you normally create a mode, you have some terminal that is a macroscopic system in 3 dimensions and which tends to be thermalized. And then if you just have a single chiral mode going out, it's automatically thermalized to begin with. And so it's experimentally untestable question, what happens there beyond thermal equilibrium? If you have multiple modes, especially contra-propagating modes, but even co-propagating modes, because you can drive them from different terminals, then all sorts of interesting thermalization questions emerge. But then your physics applies. So maybe the point is not even the lack of thermalization, but that the situation I'm asking is entirely irrelevant for the sort of questions you are asking.
Yes. Yeah, that might be. Yeah. Thank you. Okay, so in this case where we have two different velocities, the thermoelectric effects actually don't do much because you can show that kind of interactions between these two KPZ modes are kinematically disfavored. They don't really want to talk to each other. When they are the same velocities, there's some interesting effects. So it would be interesting if there's a situation where they're exactly the same, but there's still thermalization. I don't know if that's a very natural setting though. Okay, but in the general case where they're different, so basically the same story holds both for the heat mode and for the charge mode. or whatever, you know, the diagonalized modes are when they're thermoelectric effects. And so you have kpz spreading of both modes and these singular connectivities. One special case is when the bulk thermal Hall connectivity vanishes, as is the case, for example, for n equals 2/3. So then the heat mode no longer propagates chirally. And at the linearized level, you would just say that it diffuses in that case. So that was what was found in this paper, that you simply have diffusion of heat and then charge does its kpz thing. So we could ask, does this prediction also survive, does this prediction survive against hydrodynamic fluctuations? And the answer is again, no, even though in this case, heat doesn't have any self-interactions, because these important self-interactions came from the ballistic parts, and it's not propagating ballistically. But it does couple to discharge, which is strongly fluctuating. And because of this coupling, it actually changes the dynamics of heat. And so actually this equation is an open problem in stochastic physics. People don't know what exactly the universality class of this is. But there's an approximation called the mode coupling approximation, which actually agrees pretty well with numerics for this problem, which predicts that the dynamic critical exponent in this case is 5/3 instead of 2 for diffusion. So even in this case, we don't have diffusion. Heat still spreads, but slightly differently than with diffusion. And the optical connectivity in this case is actually a bit more singular because of this very soft heat mode. All right, so let me say a few words about experiments. First, a cautionary comment is that probably most of the people in the audience know much more about experiments in quantum Hall systems than I do. So I really hope that you can give me some input on perhaps, you know, better ideas to access this physics. So the two main predictions we had are this singular edge connectivity and the anomalous damping of edge modes. This optical connectivity, I expect, is probably pretty difficult to see because, you know, it's usually how we measure optical connectivities with reflectance measurements, but this in 1D is hard. Maybe you can imagine stacking your systems and seeing it, but I expect this will be pretty hard. But the anomalous damping of edge modes seems quite accessible. In fact, these edge modes called edge magnetoplasmons have been observed for a very long time, in '92 in gallium arsenide, and also more recently in graphene and cold atoms. So here you can even see this edge mode kind of damping with as it goes around the droplet. And so here we could, in principle, test our prediction for the damping of these edge modes. So we have a prediction for the, first of all, the filling dependence, a simple linear infilling dependence of the damping of this mode. This has been widely observed experimentally, that the damping depends on filling in this way. The temperature dependence is rather weak in our expression, and that seems more or less consistent with experiments. But probably the most striking of our predictions is this dependence on the wave vector or the frequency, how the damping depends on frequency. And this, it seems, hasn't been studied too much in experiments. We only found one paper, which actually is very promising, but it's a pretty old paper. And what they found is that the magnitude of the damping increases with frequency, the dependence being somewhere between linear and quadratic. And that's very nice because 3/2 is provably between linear and quadratic. So that seems promising, but it would be nice to have a kind of more modern experiment test these things. Heat, of course, is difficult, but it's a bit easier to observe heat when there's upstream heat transport, when the Hall connectivity, the thermal Hall connectivity vanishes, so that it's kind of the only thing that's moving upstream. So in this case, we have a prediction for the dynamics of heat, which is non-diffusive, and you could imagine using these that this might be accessible through the experiments that measure upstream heat transport. All right, let's see, how am I doing with time? Just check.
Out.
Oh, I'm out. Okay, sorry. So maybe let me stop here. Yeah, the last thing was just on these chiral surface metals. Yeah, so let me stop here and take questions. Thanks a lot for your attention.
Okay, questions.
Hi, can I ask a question real quick?
Yep.
Hey, Luca. It's good to see you.
Oh, hey, how's it going?
So you commented a little bit about your expectations for, I think you said, lack of diffusion in these chiral systems.
Mm-hmm.
Or I guess these single mode chiral systems is what
yeah.
is the case, right?
Yeah.
I was wondering if you could elaborate a little bit more on that, exactly what you
mean.
Yeah.
So well, let me give you one example. Is a CFT or any CFT, any 2D CFT. In a certain sense, I would say that any 2D CFT doesn't thermalize because thermal correlation functions in a 2D CFT are completely fixed by symmetries, and you never have hydrodynamics. Everything is kind of on the light cone. If you tried to compute a speed of sound, you would find 1 in relativistic units. And so clearly you can't have diffusive spreading around this. So that's an example of a system that I would say doesn't thermalize because it doesn't lead to emergence of hydrodynamics, a 2D CFT. It's not the case in higher dimensions for CFTs. And so that's kind of the underlying reason also why these chiral-Oettinger liquids, pure chiral-Oettinger liquids don't thermalize. Now, if you have counterpropagating modes and you add interactions between them, there you can definitely have a thermalization, but that would be kind of an irrelevant deformation on top of your CFT, for example.
Sorry, so you're saying that so if I had some pure CFT, mm-hmm. I could compute its 2-point function, say of some current that I had in the theory.
Yeah.
And you're saying that obviously I just won't see diffusion in that object.
Right. Yeah.
And obviously that's immediately true on the plane. I imagine. Yeah,
let me take the thermodynamic limit. So infinite volume,
okay,
but finite temperature. Yeah.
Okay. Yeah. Gotcha. I had another question, but I can let other people go first. But
yeah.
May I ask you if there is much difference when you introduce long-range interactions? So Coulomb interactions say in this lattice-liquid game differs from K-square weakly enough that people typically just mimic at very normalized velocity. But I wonder if something more interesting comes in your picture.
Yeah, it's not much more interesting. So it does lead to some kind of logarithmic corrections. But it doesn't really change. Yeah, it doesn't really change the answer.
Mm-hmm. So, and another question that's motivated by what happens in real samples. Mm-hmm. So it's very typical for this stuff to leak heat into the bulk. The physics of that is not well understood. And apparently a very big difference comes from how much metal is around, but it doesn't have to be exactly nearby. But there are samples where the heat is dissipated almost immediately. And so the only conserved quantity is charge. Right. So I wonder how would your picture deal with that? Because strictly speaking, you don't have a closed system. You never have a closed system here because the bulk is never gapped. It's a very nice theoretical approximation, but no single sample with truly gapped bulk was ever built, I believe. Maybe Manfred and his interferometry experiments approach that. But even this is a subtle question, and his samples are pretty small. Generally the bulk is not gapped, so you definitely leak heat into the bulk. So how would this modify the picture?
Yeah, so it's a game of timescales. I mean, if heat is not conserved at all, then all I said about charge will still apply, and you just simply won't have another slow mode. And then it's a question of timescales. So is the lifetime of heat longer than the thermalization time or not? If it is, then you might have a window where you see this physics before heat has the time to leak out. And kind of at the level of equations, you would just kind of model it with a relaxation rate for heat, and that would really, put an IR cutoff on all this IR stuff happening. It would protect you from seeing KPZ. at total times.
It's not at all clear how to model that relaxation rate.
Right.
It seems that it is very strongly energy dependent. So perhaps one should introduce different rates for different energies. So it's extremely messy.
I see. So when you say energy dependent, you mean on the
well, experimental data extremely limited, but what data exist show insane dependence of that effect on the temperature.
I see.
To the extent that in some class of samples, it looks like that there is a critical temperature of between 30 and 40 milli-K, and above 40 milli-K, you have a very significant loss. Below 30, much smaller loss. And when you go above 100 milli-K, it seems that this loss is a single dominant process. You don't really have edge physics. So, and then you don't find theoretical papers that just tell, let's consider a coupled bulk edge system. Every theoretical paper considers the edge, all these classical papers by Ken and Fisher. It looks like that above 100 milli-K, you really just, your main effect is that the heat somehow disappears under the bulk almost immediately. Don't know what to make of that. And different groups have different physics. So I think multi-hybrid samples have a relatively well-isolated edge. Amir-Jacobi samples somehow lose heat very fast, and so on. Jim Eisenstein built a sample which was losing heat very quickly, and he figured out why. As it turns out, he had very much metal right along the edge, so it was lost not on the bulk of the sample, it was lost to the metal on the surface of the sample. So there are so many things, and it's hard to tell what is fundamental physics, what is device engineering.
Right. Yeah.
Can I ask real quick, Luca, if you probably a rather obvious question. Do you have an ADS picture of any of this?
So yeah, so fluctuation effects are usually 1/n suppressed. They're suppressed by the equation of states, by the free energy. So in holography, they're hard to see. And in higher dimensions, they have been seen. You have to compute some loop in the bulk. But in higher dimensions, there's small effects, even if n is not large. So you could ask, okay, in 1 + 1D, there should be something dramatic that happens. There should be a non-commutativity of the limits of n goes to infinity and low frequencies, meaning a graviton loop in the bulk should give you a correction that's 1/n suppressed, but that's dominating. That's a lower power frequency than the leading answer. And I don't think this has been done much. I mean, there's a lot of 2D, 3D holography for CFTs with BTZ black holes, but here you really need to go away from the CFT to have hydrodynamics. So you need a relevant deformation, and there isn't much on this. Yeah, it would be interesting.
Yeah, right. And I mean, I guess here a fundamental role is played by the anomaly, right? So you know that you would want some kind of a Chern-Simons coupling in the bulk.
Yes. Yeah, it depends what your question is. If you just want to see KPZ physics, you can also do that with momentum conservation. I had my condensed matter hat on and wanted to forget about momentum conservation. But if you're just asking about KPZ physics, this you could have with momentum conservation, and then you could just ask in a regular, pretty standard ADS picture how to see this. But yeah, otherwise getting this anomaly from ADS isn't too hard. You probably just have a Chern-Simons term.
Sure. Yes. Yeah. But sorry, so you're saying that to just see, if I want to define some correlation function that has KPZ scaling, you're saying that there are other ADS setups that you would look at for that kind of a thing?
Yeah.
Gotcha.
What you need for KPZ is a ballistic mode in 1 dimension. So regular, fluid hydrodynamics does this, should do this in 1 dimension.
I see. Yeah. Thanks.
Yeah.
Last chance to ask a question.
Well, I think we are badly over time, so
it's online. We have no upper limit. So
well, I'm not sure. At some point, people will begin disappearing.
People have already disappeared.
Looks like they actually
ago.
did. Almost no one is left. Actually, they did.
Yeah. So that's why there is no lower limit. I mean, if
there's no shame. You don't watch them walk out of the room.
Yeah. So if there are last questions, feel free to ask or remain silent forever.
Maybe I have one question.
Yeah.
How can you think of any setup that you can see you can actually see the charge and the heat have different velocity?
Mm-hmm.
Like what kind of setup or experiment that you can see that is very curious?
Yeah, well, it's probably hard to, my understanding is that it's very hard to see heat when it's not going upstream, because then I don't know if there are ways to do that.
You have an audience where there's like, this is the only audience that you can probably have a chance to have an answer to this question.
I see. Yeah. Yeah, so you guys probably know better. I mean, if there's a way to, yeah.
Okay, well, I have a question to you, but I would rather send by email. It's not directly related to the talk. Okay, so thanks a lot for giving a nice talk. Thanks, to the rest of you guys for coming.
Thank you.
It was nice to see you all.
It was very nice talk. So very
nice
very
talk.
interesting way to look at things.
Right.
Nice talk.
Bye, guys.
Yeah.